Dear students, hello. In this video, we are going to present exercises on the limit of a numerical function when x approaches a real number L. Exercise 1. Determine the following limits. 1. The limit of the expression -2 times x squared minus x plus 3 divided by x minus 1 when x approaches 1. 2. The limit of the expression x squared plus 4 times x divided by -x squared minus 2 times x plus 8 when x approaches -4. 3. The limit of the expression x squared minus 4 divided by the square root of 2 minus the square root of x when x approaches 2 from values strictly greater than 2. 4. The limit expression the square root of 9 minus x divided by x squared minus 81 when x approaches 9. Exercise 2. Let f be the function defined on the set of real numbers except -2 and 1. By f of x equals the quantity x squared plus 5 times x plus 1 divided by the quantity x squared plus x minus 2. How many asymptotes does the graph of this function have? Determine their equations. Exercise 3. Let f be the function defined on the set of real numbers excluding -1 and 1 by f of x equals 3 times x squared minus 4 divided by x squared minus 1, and let CF be its representative curve. 1. Show that CF has a horizontal asymptote. 2. Study its position relative to this asymptote. 3. Determine the limit of f of x when x approaches 1 from values less than 1, and the limit of f of x when x approaches 1 from values greater than 1. 4. What can be concluded from this? 5. Is there another value for which this is also true? While waiting to continue the video, don't forget to subscribe, like, and share the video, as well as leave comments. Exercise 1. If we directly replace in this expression x by 1, we notice that the numerator and the denominator will tend toward 0. As it is, we have an indeterminate form. Let us try to factor -2 x squared minus x plus 3. The discriminant is equal to b squared minus 4ac, so it is equal to -1 squared minus 4 times -2 times 3, which gives 1 plus 24, therefore equal to 25, which is greater than 0. There are therefore two real roots. x1 equals -b plus the square root of delta over 2a, which equals 1 plus 5 all over -4, thus equal to 6 over -4. Hence, x1 equals -3 halves. x2 equals -b minus the square root of delta all over 2a equal to 1 minus 5 over -4, therefore equal to -4 over -4. Hence, x2 equals 1. Thus, the expression becomes -2 times the quantity x minus 1 times the quantity x plus 3 halves all over x minus 1, which equals -x minus 1 times the quantity 2x plus 3 all over x minus 1, simplifying. So, for all x different from 1, we find -2x plus 3. Then, the limit when x tends toward 1 of -2x squared minus x plus 3 over x minus 1 is equal to the limit when x tends toward 1 of negative 2x plus 3, which gives negative 2 plus 3, therefore, negative 5. 2. Here again, if we directly replace x with negative 4 in this expression, we observe that both the numerator and the denominator tend towards 0. As it stands, we are dealing with an indeterminate form. X squared plus 4 times x is equal to x multiplied by the quantity x plus 4. We factor the denominator. So, the discriminant of the polynomial negative x squared minus 2 times x plus 8. Delta is equal to b squared minus 4 times a times c, which is equal to negative 2 squared minus 4 times negative 1 times 8, which equals 4 plus 32, therefore equal to 36. Since the discriminant is greater than 0, there are two roots. x1 is equal to negative b plus the square root of delta all over 2 times a, which equals 2 plus 6 all over negative 2. So, x1 is equal to negative 4. In the same way, we find that x is equal to 2. Therefore, x squared plus 4 times x all over negative x squared minus 2 times x plus 8 is equal to x times the quantity x plus 4 all over the quantity negative x minus 2 times the quantity x plus 4. As a result, for all values of x different from negative 4, the limit as x approaches negative 4 of x squared plus 4 times x over x squared minus 2 times x plus 8 is equal to the limit as x approaches negative 4 of negative x over x minus 2, which gives negative 2/3. Three. When we replace x with 2, we obtain 0 divided by 0, which results in an indeterminate form. X squared minus 4 is equal to x minus 2 times x plus 2. We multiply both the numerator and the denominator by the conjugate expression, namely, the square root of 2 plus the square root of x. We factor out the negative sign as a common factor and obtain negative of 2 minus x times x plus 2 times the square root of 2 plus the square root of x, all over 2 minus x. This simplifies by canceling out 2 minus x, which gives negative of the square root of 2 plus the square root of x times x plus 2. Therefore, the limit as x approaches 2 from above of x squared minus 4 over the square root of 2 minus the square root of x is equal to the limit as x approaches 2 from above of the negative of the square root of x plus the square root of 2 times x plus 2, which gives negative 8 times the square root of 2. Four. Problem statement. We want to study the following limit: the square root of 9 minus x divided by the square of x minus 81. As x approaches 9 from values strictly less than 9. Again, if we substitute x with 9, we notice that both the numerator and the denominator tend towards 0, which results in an indeterminate form. Step 1. Factoring the denominator. Let's start by rewriting the denominator. The square of x minus 81 can be rewritten as a special product, namely, x minus 9 multiplied by x plus 9. So the expression becomes the square root of 9 minus x divided by the product of x minus 9 and x plus 9. Now observe that the difference x minus 9 can be rewritten as -1 multiplied by 9 minus x. Also, 9 minus x can be written as the square root of 9 minus x, all squared. Step 2. Simplification. We now observe that the square root of 9 minus x appears both in the numerator and in the denominator, in squared form, which allows us to simplify the quotient. So for any x different from 9, and after simplification, we obtain -1 divided by the square root of 9 minus x, then multiplied by x plus 9. Step 3. Studying the limit. As x approaches 9 from smaller values, the difference 9 minus x tends towards 0 through strictly positive values, so the square root 9 minus x tends towards 0 but remains positive. X plus 9 tends toward 18. Then the expression becomes -1 divided by a very small positive number, multiplied by 18. And what happens when we divide by a very small positive number? The quotient becomes a very large number in absolute value, but negative, because of the -1 in the numerator. Exercise 2. In this exercise, the goal is to find the asymptotes of the graph representing the function f. Analysis of the limits and asymptotes of the function f. Let us first study the limits as x approaches positive infinity and negative infinity. According to the limit of the quotient of the highest degree terms, the limit of f of x as x approaches positive infinity is equal to 1. Similarly, the limit of f of x as x approaches negative infinity is also equal to 1. Therefore, the graph of the function f has a horizontal asymptote with the equation y equals 1. Now let us study the limits near -2. The denominator is a second-degree polynomial with roots -2 and 1, so positive when x is less than -2 or greater than 1, and it is negative when x is greater than -2 and less than 1. A limit as x approaches -2 of the expression x squared plus 5 times x plus 1 is equal to -5. And the limit as x approaches -2 from the left of the expression x squared plus x minus 2 is equal to 0 from strictly positive values because x is less than -2. Therefore, the limit of f of x as x approaches -2 from the left is equal to -infinity. Similarly, a limit of f of x as x approaches -2 from the right is equal to positive infinity, because x is greater than -2 and the denominator tends to 0 through strictly negative values. Finally, let us study the limits near 1. The limit as x approaches 1 of the expression x squared plus 5 times x plus 1 is equal to 8. And the limit as x approaches 1 from the left of the expression x squared plus x minus 2 is equal to 0 from strictly negative values, because x is less than 1. Therefore, the limit of f of x as x approaches 1 from the left is equal to -infinity. Similarly, the limit of f of x as x approaches 1 from the right is equal to positive infinity. Thus, the graph of the function f also has two vertical asymptotes, with the equations x equals 1 and x equals -2. While waiting to continue the video, don't forget to subscribe, like, and share the video, as well as leave comments. Exercise 3. Let us consider the function named f, which is defined on the set of all real numbers except for -1 and 1. This function is given by the following expression: 3 times the square of x minus 4, the whole divided by the square of x minus 1. We will denote by CF the graph representing this function. 1. Showing that the graph CF has a horizontal asymptote. Study of the limit at infinity. We begin by examining the behavior of the function when the variable takes on very large values, either positive or negative. We observe that as the variable becomes very large in the positive or negative direction, the quotient of the highest degree terms in the expression of the function approaches a certain number. More precisely, the numerator contains 3 times x squared minus 4, while the denominator contains x squared minus 1. When x becomes very large, the terms -1 and -4 become negligible. So we can say that the quotient tends toward 3. Therefore, we conclude that the graph of the function has a horizontal asymptote, which means a line that the curve gets closer and closer to as we move farther out in the positive or negative direction. The equation of this line is y equals 3. 2. Determining the limit of the function as the variable approaches 1 from the left and then from the right. Study of the sign of the difference between the function and this asymptote. We now examine of the difference between the function and the horizontal asymptote. To do this, we subtract 3 from the expression of the function and simplify. We obtain a new expression that is equal to -1 divided by the square of x minus 1. The sign of this expression depends on the sign of the polynomial in the denominator, which is the square of x minus 1. This polynomial is positive for values less than -1 or greater than 1, negative for values strictly between -1 and 1. This means that the function is above the horizontal asymptote for values of the variable strictly between -1 and 1, and below this asymptote for very large or very small values outside the interval from -1 to 1. Three. Determining the limit of the function as x approaches 1 from the left, then as x approaches 1 from the right. Behavior around the value 1. We now study what happens when the variable approaches the value 1. First, from the left, that is, with values slightly smaller than 1, and then from the right, with values slightly larger than 1. If we replace x in the numerator with a value just less than 1, we get -1. In the denominator, we get a value approaching 0 but negative, since it is negative between -1 and 1, except at the roots. Therefore, as we approach 1 from the left, the expression becomes a division by a very small negative number, which gives a result that becomes very large and positive, tending toward positive infinity. When approaching 1 from the right, we divide by a very small positive number, which gives a result that becomes very large but negative, tending toward negative infinity. 4. What can we conclude from this? In conclusion, the function becomes infinitely large or infinitely small when approaching 1. This means that the graph has a vertical asymptote at x equals 1. 5. Is there another value for which the same is true? Study of the behavior around the value -1. We repeat this analysis, this time around the value -1. When approaching -1 from the left, we divide by a small positive number because the denominator is positive outside the roots and negative between them. This causes the function to become very large but negative. When approaching -1 from the right, we divide by a small negative number, which causes the function to become very large but positive. Therefore, we conclude that the function becomes very large or very small around the value -1, which means that the graph also has a vertical asymptote at x equals -1. Final conclusion. The graph represents a rational function that has two vertical asymptotes where the function becomes infinite, has a horizontal asymptote which reflects the value the function approaches at infinity. Between the vertical asymptotes, the graph changes position relative to the horizontal asymptote. On either side, the function remains below this horizontal asymptote. At the end, dear students, I thank you for your attention, and in the next video, I say goodbye to you.